I've been thinking a lot about the moon lately, and it's strange, isn't it, how we take it for granted. It's just there, right? Every night, or most nights anyway, this luminous disk hanging in the sky, sometimes full and bright, sometimes a delicate crescent, sometimes hidden entirely. We've grown up with it, all of us, and our ancestors saw the same moon, and their ancestors before them, going back thousands and thousands of years. It's so familiar, so constant, such a basic part of our experience of the night sky that we rarely stop to think about what it actually is, where it came from, why it's there at all. But here's the thing, and this is what I find so fascinating, so deeply mysterious when you really start to dig into it. The moon shouldn't exist, not in the way it does, not where it is, not with the relationship it has to Earth, not with the profound influence it exerts on everything about our planet and, well, about us. The moon has a secret history, you see, a story that's written in rocks and physics and mathematics. And when you start to uncover that story, when you really look at what we've learned about our nearest celestial neighbor over the past few decades especially, it becomes clear that the moon isn't just a pretty thing to look at, isn't just a romantic backdrop or a curiosity. It's central to everything. It's part of Earth's biography in ways that are difficult to fully comprehend, and the history of how it got there, how it came to be, is one of the most violent, catastrophic, and ultimately beautiful stories in the entire history of our solar system. So let me start with what we think we know, with what seems obvious. The moon orbits Earth, right? It takes about 27 days to go around us, and as it does, we see different portions of its sunlit face, which gives us the phases, the cycle from new moon to full moon and back again. It's about 250,000 miles away, which sounds like a lot, and it is, but in cosmic terms, it's right next door. It's so close that we could see it with our own eyes when humans finally went there, could watch it growing larger in the windows of the spacecraft, could walk on its surface and look back at Earth hanging in the black sky. And that's remarkable, right? That humans have actually been there, have touched it, have brought pieces of it back. But even before we went there, even before we had telescopes, people were looking at the moon and wondering, what is that thing? Why does it change shape? Why does it move across the sky? Ancient cultures built entire mythologies around it. They noticed patterns, tracked its movements, used it to mark time. The moon was a god, a goddess, a chariot, a face, a bowl, a mirror. Every culture that ever looked up had a story about the moon. And those stories, well, they tell us something about how fundamental it is to human experience, how long we've been trying to understand it. The thing is, for most of human history, we had it all wrong. Not about the obvious stuff, not about the phases and the cycles, people figured that out pretty early on, but about what the moon actually is, where it came from, how it relates to Earth. For a long time, people thought it was just another celestial object, maybe made of some kind of special ethereal substance, maybe a perfect crystalline sphere like Aristotle imagined all celestial bodies to be. Even when we started doing real astronomy, when people like Galileo turned telescopes toward the moon and saw mountains and craters and realized it was a world, an actual rocky world like Earth in some ways, we still didn't really understand. We didn't know how it formed. We didn't know why it was there. There were theories, of course. There are always theories. Some people thought maybe the moon formed at the same time as Earth, condensing out of the same cloud of gas and dust, like siblings born together. Others thought maybe the moon was captured. Maybe it formed somewhere else in the solar system and then, through some gravitational interaction, got caught by Earth's gravity and ended up in orbit. There was even a theory, and this one's kind of wild, that the moon was actually part of Earth originally, that it somehow spun off or broke away, that there's a scar on Earth where the moon used to be. Some people pointed to the Pacific Ocean basin and said, see, that's where it came from, that's the hole it left behind. But here's the thing about those theories, all of them, they don't really work. I mean, they sound plausible, sort of, if you don't look too closely. But when you actually run the numbers, when you look at the physics and the chemistry, when you examine the evidence, they fall apart. The co-formation theory, the idea that Earth and Moon form together, it can't explain why the Moon has almost no iron core compared to Earth, why its density is so different, why its composition isn't more similar to ours. The capture theory has even bigger problems, because capturing a body as large as the Moon is incredibly difficult, incredibly unlikely. You'd need just the right speed, just the right angle, just the right circumstances. And even then, the orbit you'd end up with wouldn't look like the Moon's orbit. It would be highly elliptical, probably tilted at a crazy angle, and it would be unstable. The moon's orbit is too circular, too regular, too perfect to be the result of a capture. And that fission theory, the idea that the moon spun off from Earth, well, it sounds dramatic, but there's no mechanism for it, nothing that could make that happen. Earth would have had to be spinning impossibly fast, and even then, the physics don't work out. The angular momentum is all wrong. The chemistry doesn't match. So for a long time, we had this problem. You see, we had the moon, we could observe it, we could measure it, we could even eventually go there and walk on it and bring back samples. But we couldn't explain it. Every theory had fatal flaws. And that's frustrating, right? When you can see something, when it's right there in front of you, when it's so close and so obvious, but you can't figure out how it came to be. It's like finding a building in the middle of a desert with no roads leading to it, no sign of how it was constructed, no explanation for why it's there. The moon was our mystery, and it took a combination of observations and experiments and computer simulations and, well, some really creative thinking to finally crack it, to finally understand what happened. And when we did understand, when the pieces finally came together, the story that emerged was so much stranger and more violent than anyone had imagined. The answer, it turns out, involves a collision, not a small collision, not a gentle bump, but a catastrophic impact on a scale that's difficult to comprehend. We're talking about the early solar system here, about 4.5 billion years ago, when Earth was still young, still forming, still hot and partially molten from the energy of all the smaller impacts that had built it up over millions of years. The solar system back then was a chaotic place, you have to understand. It wasn't the orderly, stable system we see today, with planets in neat orbits and mostly empty space in between. No, it was crowded with debris, with chunks of rock and metal ranging in size from pebbles to planets, all swirling around the young sun, all colliding with each other, merging, breaking apart, gradually assembling into larger and larger bodies through the process we call accretion. Earth was one of those bodies, growing larger with each impact, and there were others too, other planet-sized objects forming in roughly the same region of the solar system. And one of those objects, one of those protoplanets, we call it Theia, named after the Greek Titaness, who was the mother of the moon goddess Selene. Appropriate name, given what was about to happen. Theia was probably about the size of Mars, maybe a little bigger, maybe a little smaller. Estimates vary, but we're talking about something big, something substantial, something with enough mass to have its own gravity, its own differentiation into a core and a mantle. It was orbiting the sun in roughly the same region as Earth. And over time, over millions of years perhaps, the orbits evolved, influenced by gravity, by the presence of Jupiter farther out, by all the complex gravitational interactions that govern the solar system, and eventually, inevitably, their paths crossed. Theia hit Earth. Not a head-on collision, thankfully, or we wouldn't be here. If Theia had hit Earth straight on, both objects probably would have been completely destroyed, shattered into pieces that would have either dispersed or recoalesced into something entirely different. No, this was a glancing blow, an impact at an angle, with Theia striking Earth off-center. And that angle, that specific geometry of the collision, that's what made all the difference. It's what allowed the moon to form. Try to picture this for a moment, even though it's almost impossible to really grasp the scale. Imagine an object the size of Mars, thousands of miles across, ploughing into Earth at something like 25,000 miles per hour, maybe faster. The energy released in that impact was, well, it's beyond anything we can compare to human experience. We're talking about energies that would make all the nuclear weapons ever built look like firecrackers. The collision vaporized rock, turned solid material into gas and plasma, sent shockwaves through both bodies that would have melted and shattered and reorganized matter on a planetary scale. Part of Theia's core probably merged with Earth's core, sinking down through the molten rock because of its density, because iron and metal are heavy and they fall inward. But part of Theia, especially the outer layers, the mantle material, along with a significant portion of Earth's own outer layers, all that material was blasted out into space by the force of the impact. It formed a cloud, a disk of vaporized and molten rock orbiting Earth, unimaginably hot, glowing, spreading out around the young planet like a ring. And from that disk, from that debris, the moon formed. It happened relatively quickly in geological terms, maybe over a few decades, maybe a century, maybe 1,000 years, we're not entirely sure, but quickly compared to the millions of years it took for Earth and Theia to form in the first place. The material in the disk was orbiting Earth, and as it cooled, as the vaporized rock condensed back into liquid and then into solid particles, those particles started to collide with each other, to stick together, to accumulate through gravity into larger and larger clumps. This is accretion again, the same process that built the planets, but happening in miniature, or not so miniature really, because the final result was the Moon, a body over 2,000 miles in diameter, massive enough to be round, to have its own gravity shape it into a sphere. And it formed right there, in orbit around Earth, out of material that had been part of both Earth and Theia, blended together in that catastrophic impact, mixed and melted and reformed into something new. This theory, this idea of a giant impact creating the Moon, it's called, appropriately enough, the giant impact hypothesis, or sometimes the big splat, which is a bit more playful but captures the drama of it, and it wasn't always the accepted explanation. It emerged gradually, developed over decades as scientists gathered evidence, ran computer simulations, analyzed lunar samples. The first real hint came from the Apollo missions, actually, when astronauts brought back rocks from the Moon, and scientists could finally study them in detail, could analyze their composition, their mineralogy, their isotope ratios. And what they found was both similar to Earth and different in important ways. The Moon rocks were made of the same kinds of minerals you find on Earth, which suggested a connection, a relationship, a shared origin maybe, but they were also depleted in volatile elements, things like water and carbon and nitrogen, things that evaporate easily at high temperatures, and they were depleted in iron. The Moon has much less iron proportionally than Earth does, which is why its overall density is lower. If the Moon had formed from the same material as Earth in the same proportions, it should have more iron. But it doesn't, and that was a clue. Another clue came from oxygen isotopes. Different objects in the solar system have different isotope ratios, different proportions of oxygen-16 versus oxygen-17 versus oxygen-18, and these ratios are like fingerprints. They tell you where something formed, what kind of material it came from. Meteorites from Mars have one signature. Meteorites from asteroids have different signatures. And when scientists measured the oxygen isotopes in Moon rocks and compared them to Earth rocks, they found something surprising. They were almost identical. Not just similar, but nearly indistinguishable. And that's strange, you see, because if the Moon had formed somewhere else in the solar system and then been captured by Earth, or if it had formed independently even in roughly the same orbit, you'd expect a different isotope signature. The fact that Earth and Moon have the same signature suggests they formed from the same material, or from material that was mixed together very thoroughly. And that's exactly what the giant impact hypothesis predicts. When Theia hit Earth, when the material from both bodies was vaporized and melted and mixed together in that debris disk, the isotopes would have been homogenized, blended together into a uniform composition. The computer simulations really sealed it, though. As computers got more powerful, as scientists developed more sophisticated models of impacts and orbital dynamics and material behavior, they could simulate the giant impact, could model what would happen if a Mars-sized object hit Earth at different angles, different speeds, different compositions. And what they found was that certain scenarios, certain specific impact parameters, produced results that matched what we observe. A glancing blow at just the right angle, with just the right velocity, would indeed throw enough material into orbit to form the Moon. It would produce a Moon with the right mass, the right composition, the right orbit. Not every simulation worked. Many produced moons that were too small or too big or had the wrong composition. But some simulations, the ones with parameters that were geologically plausible, given what we know about the early solar system, those produced something that looked remarkably like our Moon. And that's powerful evidence, you know. When your theory not only explains the existing observations, but also makes predictions that turn out to be correct when you simulate it, that's when you start to gain confidence that you're on the right track. But let's think about what this means, what this story of the Moon's origin tells us. First of all, it means Earth itself was profoundly changed by this impact. Before the collision, Earth was already here, already forming, already substantial. After the collision, it was different. It had incorporated much of Theia's mass, particularly Theia's iron core, which sank down and merged with Earth's core. That changed Earth's size, its mass, its composition. The impact also would have melted much of Earth's surface, maybe melted the entire planet down to significant depths. Any atmosphere that existed before the impact would have been blown away. Any water would have been vaporized. Any early crust would have been shattered and reformed. Earth essentially had to start over in some ways, had to re-solidify, re-differentiate, reform a crust, and eventually, much later, reaccumulate an atmosphere and oceans. The giant impact was a reset button, a catastrophic event that reset Earth's evolution. And yet somehow out of that violence, out of that destruction, came something that would turn out to be essential for life, essential for Earth's long-term habitability. The moon. Because the moon, you see, isn't just a pretty object in the sky. It's not just a curiosity, not just something nice to look at. The moon has shaped Earth's history in fundamental ways, has influenced our planet's evolution, has affected the development of life itself. And the first, most obvious way it does this is through tides. Everyone knows the moon causes tides, right? We learn that in school. The moon's gravity pulls on Earth, pulls on the oceans, and that creates the rise and fall of sea level that we call tides. But there's more to it than just the simple picture of the moon pulling water toward itself. Tides are actually caused by the difference in gravitational force across Earth's diameter. The side of Earth closest to the moon feels a stronger pull than the center of Earth, and the center feels a stronger pull than the far side. This difference, this gradient in gravitational force, it stretches Earth, deforms it slightly, creates a bulge of water on both the near side and the far side. And as Earth rotates, as different parts of the surface pass through these bulges, we experience high and low tides. Now, you might think, okay, tides, that's interesting, that affects the ocean, affects beaches and boats and marine life. But it's not that big a deal, right? Except it is. It's a huge deal. Tides don't just affect the oceans, they affect the solid Earth too. The rock itself is deformed by tidal forces, flexed and stretched, not by much, just a few inches, but it happens. And this constant flexing, this tidal deformation, it creates friction, generates heat, dissipates energy. And that energy has to come from somewhere. It comes from Earth's rotation. The tides are actually slowing Earth's rotation down, gradually, imperceptibly, but measurably. Every century, the day gets a little bit longer, about 1.7 milliseconds longer per century, which doesn't sound like much, and it isn't on human timescales, but over geological time, over billions of years, it adds up. 4 billion years ago, when the moon first formed, Earth's day was probably only about 5 or 6 hours long. Earth was spinning much faster back then. Since then, tidal friction has slowed us down to our current 24-hour day, and this process is still happening. In the far future, if we wait long enough, Earth's rotation will slow down even more until eventually Earth will become tidally locked to the moon, just as the moon is already tidally locked to Earth. That's another fascinating piece of this, you see. The moon always shows us the same face. You've probably noticed this if you've ever looked at the moon carefully. The pattern of dark and light areas, the Maria and the highlands, they're always the same. We always see the man in the moon or the rabbit or whatever pattern your culture sees, and it's always in the same position. That's because the moon's rotation period exactly matches its orbital period. It takes the same amount of time for the moon to spin once on its axis as it takes to orbit Earth once, about 27 days for both, and this isn't a coincidence. It's the result of tidal locking, the same process that's slowing Earth's rotation. But in the moon's case, it happened much faster because Earth's tidal forces on the moon are much stronger than the moon's tidal forces on Earth. Earth is 80 times more massive than the moon, so its gravitational influence is much greater. Over time, as the moon orbited Earth, Earth's tidal forces created bulges in the moon, and those bulges, through friction, slowed the moon's rotation down until it became synchronized with the orbit. And now the moon is locked, permanently showing us the same face, with the far side, the side we can't see from Earth, remaining hidden. We didn't even know what the far side looked like until the space age, until we sent probes that could orbit the moon and photograph the hidden hemisphere. But here's something even more remarkable, something that doesn't get talked about as much. The tidal interaction between Earth and Moon isn't just slowing Earth's rotation, it's also pushing the Moon away. The same forces that slow Earth's rotation transfer angular momentum to the Moon, which makes the Moon's orbit gradually expand, gradually move farther from Earth. And this isn't hypothetical, we can measure it. Using laser ranging experiments where we bounce lasers off reflectors left on the Moon by Apollo astronauts, we can measure the distance to the Moon with incredible precision down to millimeters. And what those measurements show is that the Moon is receding from Earth at a rate of about 3.8 centimeters per year, about 1.5 inches per year. That's roughly the rate at which your fingernails grow, which gives you a nice human scale comparison. Every year, the Moon is a fingernail's length farther away. This has profound implications, doesn't it? Because if the Moon is moving away now, that means it was closer in the past, much closer. When the Moon first formed, right after the giant impact, it was probably only about 15 or 20,000 miles from Earth, compared to the 250,000 miles it is now. It would have appeared enormous in the sky, maybe 10 or 15 times larger than it appears today, and the tides it raised would have been correspondingly stronger, much stronger, hundreds of feet high perhaps, massive waves that would have swept across the early Earth's surface every few hours as the planet rotated rapidly beneath the nearby Moon. Over time, as the Moon moved away, as Earth's rotation slowed, the tides became smaller, the day became longer, the Moon became smaller in the sky. And this process continues. In the far future, the Moon will be even farther away, will appear even smaller, will raise even weaker tides. Eventually, billions of years from now, the Earth-Moon system will reach a state of double tidal lock, where not only does the Moon show the same face to Earth, but Earth will also show the same face to the Moon. Both will rotate at the same rate as the Moon's orbital period, which by then will be much longer, maybe 50 or 60 Earth days, and the Moon will hover over the same spot on Earth's surface, visible only from one hemisphere, never rising or setting, just hanging there in the sky, while the other hemisphere never sees it at all. Of course, that's billions of years in the future. And other things will have happened by then. The Sun will have evolved into a red giant, possibly engulfing both Earth and Moon. But the point is, the Earth-Moon system is dynamic, is evolving, is changing over time, and understanding that evolution, tracing it backward and forward, gives us a deeper appreciation of how intimately connected these two worlds are. They're not separate objects that just happen to be near each other. They're a system bound together by gravity and history, by the violence of their formation and the long, slow dance of their evolution. And there's another crucial way the Moon has influenced Earth, another way it's been essential for life, and that has to do with Earth's axial tilt. Earth's rotation axis isn't perpendicular to its orbital plane around the Sun. It's tilted at about 23.5 degrees, and that tilt is what gives us seasons. As Earth orbits the Sun, sometimes the northern hemisphere is tilted toward the Sun, giving us summer in the north and winter in the south, and 6 months later, the southern hemisphere is tilted toward the Sun, reversing the seasons. Without that axial tilt, we wouldn't have seasons, at least not the way we experience them. But here's the thing, that axial tilt isn't stable on its own. Without the Moon, Earth's tilt would vary wildly over time, would wobble chaotically under the gravitational influence of the Sun and the other planets, particularly Jupiter. Computer simulations show that without the Moon's stabilizing influence, Earth's axial tilt could vary from 0 degrees to 85 degrees or more, swinging from one extreme to another on timescales of millions of years. Think about what that would mean. If Earth's tilt suddenly changed from 23 degrees to 60 degrees or 80 degrees, the climate would change drastically, catastrophically. At high tilts, the poles would point almost directly at the Sun during summer, receiving continuous daylight and intense heating, while the equator would become cold and dark for part of the year. The seasons would become extreme. Ice would advance and retreat over huge areas. Ocean currents would shift. Weather patterns would be unpredictable, volatile, and this wouldn't happen just once. It would happen over and over as the tilt varied chaotically. It's hard to imagine complex life evolving and thriving under those conditions, under that kind of climate instability. Life needs stability, needs predictability, needs a relatively stable environment over long periods to evolve complexity, and the moon provides that stability. The moon's gravity acts on Earth's equatorial bulge, the slight flattening of Earth caused by its rotation, and that gravitational torque stabilizes the axial tilt, keeps it relatively constant, prevents the wild variations that would otherwise occur. The moon has given Earth a stable climate, or at least a climate that varies within predictable bounds, and that stability has been crucial for the evolution of life. So when we talk about the moon's secret history, we're not just talking about a story of how a chunk of rock came to orbit our planet. We're talking about a story that's intimately connected to Earth's own story, to the story of life itself. Without the giant impact, without Theia hitting Earth and creating the moon, Earth would be a very different place. It would have a shorter day, maybe still just a few hours long. It would have no large moon to stabilize its axial tilt, no tides to mix the oceans and drive currents, no bright light to illuminate the night. The climate would be unstable, the seasons would be chaotic. It's possible, some scientists argue, that complex life might never have evolved at all. The moon isn't just a companion, it's a guardian, a stabilizer, a crucial part of the system that makes Earth habitable. And yet, and this is what I find so remarkable, so humbling, the moon's existence is, in some sense, an accident. It's the result of a collision, a random event, a moment of violence in the early solar system that could easily have not happened, or happened differently, with different results. If Theia had been a little smaller, or hit at a slightly different angle, or at a different speed, maybe the moon wouldn't have formed at all. Maybe Earth would have just incorporated Theia's mass and continued on alone, without a large satellite. Or maybe the collision would have been so violent that Earth itself was destroyed, shattered into pieces that dispersed or recoalesced into something entirely different. The fact that things happened the way they did, that the collision had just the right parameters to create the moon, and that the moon then had just the right properties to stabilize Earth and enable life, well, that seems almost miraculous. It makes you wonder, doesn't it, about chance and necessity, about how much of our existence depends on contingent events, on lucky accidents, on things that could easily have gone differently. But let's dig deeper into what we actually learned from going to the moon from the Apollo missions, because that's where a lot of this understanding comes from. Between 1969 and 1972, 12 humans walked on the moon, explored its surface, set up experiments, and brought back a total of about 842 pounds of lunar rocks and soil. That material, those samples, they're still being studied today, still revealing new information, and they've been absolutely crucial for understanding the moon's history and composition. Before Apollo, we had theories and speculation. After Apollo, we had data. We had actual pieces of the moon that we could hold and analyze and compare to Earth rocks and meteorites. And what that analysis revealed was both fascinating and puzzling in different ways. The lunar samples showed, first of all, that the moon's surface is incredibly old. The rocks that the astronauts collected, particularly from the lunar highlands, the bright, heavily cratered regions, are some of the oldest rocks we've ever found, dating back more than 4 billion years in many cases, to the very early history of the solar system. That's older than almost any rock on Earth, because Earth's surface is constantly being recycled through plate tectonics, through erosion and weathering and volcanic activity. Earth's oldest rocks are about 4 billion years old, but they're rare. On the moon, there's no plate tectonics, no erosion from wind or water, no volcanic activity for billions of years. The surface is frozen in time, preserving a record of the ancient solar system that's been erased on Earth. The craters that cover the moon, those scars of impacts from asteroids and comets, they date back to a period called the Late Heavy Bombardment, about 3.9 billion years ago, when the inner solar system was pummeled by debris. On Earth, those impacts happened too, but the evidence has been mostly erased. On the moon, it's still there, still visible, and we can study it. The composition of the lunar samples also confirmed what the giant impact hypothesis predicted. The rocks are made mostly of minerals like plagioclase, feldspar, pyroxene, and olivine, which are the same minerals you find in Earth's mantle and crust. But they're depleted in volatile elements and in iron, just as you'd expect if they formed from material that was vaporized and melted in a giant impact. The high temperatures of the impact would have driven off volatiles, would have caused water and other light elements to escape into space, leaving behind rock that's dry and depleted in these elements. And the iron, being dense, would have sunk to the centers of Earth and Theia during the collision, forming cores. So the material that ended up in the debris disk and formed the moon was mostly mantle rock, poor in iron. One of the most interesting findings from the Apollo samples was the discovery of what's called the lunar magma ocean. The idea is that when the moon first formed, when all that debris from the giant impact coalesced into a single body, the energy of that accretion, combined with the heat from the impact itself, was enough to melt most or all of the moon. The entire moon, or at least its outer layers down to depths of hundreds of kilometers, would have been a global ocean of molten rock, magma, glowing and hot and slowly cooling. And as it cooled, as the temperature dropped, minerals started to crystallize out of the magma, different minerals at different temperatures, and they separated according to their density. Dense minerals like olivine and pyroxene sank, forming the lunar mantle. Light minerals like plagioclase floated, forming the lunar crust, the bright highlands that we see today. This process of differentiation, of separation by density, explains the moon's layered structure and the composition of the rocks we find on its surface. And we can test this idea by looking at the chemistry of the rocks, by seeing if their compositions match what we'd predict from magma ocean crystallization. And they do. The fit is really quite good, which gives us confidence that the magma ocean really existed, that the moon really was molten shortly after it formed. The dark areas on the moon, the Maria, those smooth dark plains that form the face of the man in the moon, they have a different origin. They're younger than the highlands, dating to between about 3.9 and 3.1 billion years ago, and they're made of basalt, volcanic rock, the same kind of rock that forms the ocean floor on Earth. What happened is that after the moon formed and cooled, after the magma ocean solidified, there was still some residual heat in the lunar interior, and there were also radioactive elements like uranium and thorium that decayed over time, generating additional heat. This heat caused partial melting in the moon's mantle, and the molten rock, being less dense than the surrounding solid rock, rose toward the surface. And when large impacts occurred, when asteroids slammed into the moon and created giant basins hundreds of miles across, those basins, those low areas, became pathways for the molten rock to reach the surface. The basaltic lava flooded the basins, filling them with dark, smooth plains, covering the older, cratered terrain. That's why the Maria are dark and smooth, why they have fewer craters than the highlands. They're younger. They were resurfaced by lava flows after most of the heavy bombardment had ended. But the volcanic activity on the moon was short-lived. By about 3 billion years ago, maybe a bit later, the moon's interior had cooled enough that volcanic activity ceased. The moon is geologically dead now, has been for billions of years. There's no tectonic activity, no volcanism, no earthquakes. It's a static world, a museum of ancient history, and that's part of what makes it valuable for science. It preserves information that's been lost elsewhere, gives us a window into what the early solar system was like, what Earth itself might have looked like billions of years ago before plate tectonics and life transformed its surface. Now, there are still mysteries about the moon, still things we don't fully understand. One of the puzzles is the moon's asymmetry, the fact that the near side and far side are so different. The near side, the side we see from Earth, has large Maria, those dark basaltic plains. The far side has almost none. It's mostly highlands, heavily cratered, ancient. Why? We're not entirely sure. It might have to do with differences in crustal thickness. The far side has a thicker crust on average, which would have made it harder for basaltic magma to reach the surface, harder for volcanic flooding to occur. But why is the far side crust thicker? That's less clear. It might be related to how the moon formed, to the distribution of material in the debris disk, or it might be related to tidal forces from Earth early in the moon's history. There are theories, but it's still an area of active research. Another mystery involves the moon's internal structure. We know from the Apollo seismic experiments, from the seismometers that astronauts placed on the surface, that the moon has moonquakes, small seismic events, some caused by meteorite impacts, others by tidal stressing from Earth. And by studying how seismic waves travel through the moon, scientists have learned about its internal structure. The moon has a crust, a mantle, and probably a small iron core, maybe 200 to 400 miles in diameter, much smaller proportionally than Earth's core. But there are still questions. How liquid is the core? Is it partially molten or fully solid? Is there any convection in the mantle? Any movement of rock over geological time? These questions are hard to answer with the limited data we have, and we'd need more seismic stations on the moon, more coverage to get better answers. There's also the mystery of lunar swirls, these strange, bright, sinuous markings on the surface that look almost like someone took a paintbrush and made swirling patterns in the dust. They don't correlate with any obvious geological features, don't seem to be related to impacts or volcanic activity, and they're often associated with localized magnetic anomalies, areas where the moon's magnetic field is stronger than usual. The moon doesn't have a global magnetic field today, doesn't have a dynamo in its core like Earth does, but it did have one early in its history, and remnants of that ancient field are frozen into certain rocks. These localized magnetic anomalies might protect the surface from the solar wind, from the stream of charged particles from the sun, and that might affect the weathering of the surface, might preserve brighter, less weathered material in certain patterns. But we're not sure. It's a hypothesis, and it needs more testing, more observations. And then there are the mascons, mass concentrations, regions under the Luna Maria where the density is higher than expected, where there's more mass than you'd predict from the surface topography. These were discovered when spacecraft orbiting the moon experienced slight variations in their orbits, slight tugs from these extra dense regions below the surface. The mascons are probably related to the lava flows that filled the mare basins, to the dense basaltic rock that accumulated there. But there's more to it than that. The basins themselves, the giant impact craters that the lava filled, they might have caused upwelling in the mantle, might have brought denser material closer to the surface, and that combined with the basalt creates the mass anomaly. But again, the details are still being worked out, still being refined with better observations and better models. The point is, even after Apollo, even after decades of study, the moon still holds secrets. There are still questions we can't fully answer, still mysteries to solve. And that's exciting, isn't it? That's what science is about, always pushing forward, always finding new questions even as we answer old ones. And we are going back to the moon, After a hiatus of more than 50 years, multiple nations and even private companies are planning lunar missions, both robotic and eventually human. NASA's Artemis program aims to land astronauts on the moon again in the next few years. And this time the goal isn't just to visit and leave, but to establish a sustainable presence, to build a base, to use the moon as a stepping stone for further exploration, perhaps eventually to Mars. And as we go back, as we conduct new experiments, as we explore regions of the moon that Apollo didn't visit, particularly the polar regions where there might be water ice in permanently shadowed craters, we'll learn more, we'll refine our understanding, we'll uncover new mysteries. The presence of water ice on the moon, if it's there in significant quantities, that's a game changer for future exploration. Water is heavy, expensive to launch from Earth, and if we can find it on the moon, if we can extract it and purify it, we can use it not just for drinking and growing plants, but also for making rocket fuel. Water can be split into hydrogen and oxygen through electrolysis, and both of those are rocket propellants. A lunar base with access to water could serve as a refueling station, a place where spacecraft heading to Mars or elsewhere could stop and refuel without having to carry all their propellant from Earth. That would make deep space exploration much more feasible, much more affordable. And the moon's low gravity, only about 1/6 of Earth's, means it takes much less energy to launch from the moon than from Earth. So the moon could become a hub, a gateway, a crucial piece of infrastructure for humanity's expansion into the solar system. But all of this, all these future possibilities, they rest on the foundation of understanding the moon's past, understanding how it formed, how it evolved, how it relates to Earth. The secret history of the moon isn't just an academic curiosity. It's the key to understanding Earth's history as well, the key to understanding why our planet is the way it is, why life was able to arise and thrive here. And it's also a reminder of the violence and chaos that characterized the early solar system, the random collisions and catastrophic events that shape the worlds we see today. The solar system we inhabit, with its orderly planets and mostly empty space, is the end result of billions of years of collisions and mergers, of gravitational interactions and orbital evolutions. It's a system that emerged from chaos, and the moon is a testament to that process, a survivor of one of the most violent events in Earth's history, an event that could easily have destroyed Earth instead of creating Earth's most important companion. And I think there's something profound in that, something that speaks to the contingent nature of existence. The moon didn't have to exist. Earth didn't have to have a large satellite, didn't have to have stable axial tilt, didn't have to have the particular conditions that made it so hospitable for life. All of these things depended on specific events, specific circumstances, things that could have gone differently. If Theia had never formed or had formed in a different part of the solar system, or had collided with Venus instead of Earth, or had hit Earth at a different angle or speed, our world would be unrecognizably different. Maybe life would still have arisen, maybe not. Maybe intelligent life would have evolved, maybe not. We can't know. But we do know that the moon has been essential for Earth's stability, for the long-term habitability that allowed life to evolve from simple cells to the vast diversity we see today, including us sitting here thinking about these questions. There's also something humbling about looking at the moon and knowing its history, knowing that it's a piece of Earth in a sense, that it's made of material that was once part of our planet or part of the planet that hit us, all melted and mixed together and reformed into a new world. When you look at the moon, you're looking at a sibling, a companion born in violence, but essential for our survival. And it's still there, still orbiting, still raising tides, still stabilizing our planet, still lighting up the night sky. Every culture in human history has looked at the moon and wondered. We're still wondering, still learning, still discovering new aspects of its story. But now we have a framework, a narrative that makes sense, that fits the evidence, that explains how this unlikely companion came to be and why it matters so much. The moon is receding, moving away from us at a fingernail's pace, and that means the future of the Earth-Moon system will be different from the past. The moon will continue to drift outward, the tides will continue to slow Earth's rotation, and eventually, billions of years from now, if nothing else intervenes, the system will reach that final state of double tidal lock. Both worlds frozen in their mutual gaze, each showing the same face to the other for eternity. Or at least for as long as the sun allows, because before that happens, the sun will evolve, will expand into a red giant, will swell to many times its current size, will consume Mercury and Venus, and quite possibly Earth and Moon as well. That's the ultimate fate of our solar system, or at least of the inner part of it, about 5 to 7 billion years from now. The sun will eventually run out of hydrogen to fuse in its core, will start fusing helium, will expand and cool on the outside while heating up on the inside. The inside will become a red giant star, luminous and enormous and ultimately fatal to the inner planets. But that's so far in the future that it's hard to really grasp. 5 billion years is an incomprehensible span of time. For perspective, Earth is about 4.5 billion years old now. The moon is the same age, formed shortly after Earth itself formed. Life on Earth is about 3.8 billion years old, maybe older. The exact timing is still debated. Complex multicellular life is only about 600 million years old. Dinosaurs existed from about 230 to 65 million years ago. Humans, anatomically modern humans, have been around for only about 300,000 years. Civilization, agriculture, cities, writing, all the things we think of as human culture, only about 10,000 years. On the scale of the moon's lifetime, of Earth's lifetime, human civilization is less than an eye blink. We're incredibly recent, incredibly new, and yet here we are, trying to understand the deep history of our world and its companion, trying to piece together events that happened billions of years ago, trying to predict what will happen billions of years in the future. That's a remarkable thing, that capacity to look beyond our own brief lives, beyond our own immediate experience, to see the universe in its vast scales of space and time. And in a way, the moon helps us do that. The moon is a constant, a presence that's been there longer than life itself, longer than continents, longer than oceans, longer than the air we breathe. It's a witness to Earth's entire history, a silent observer that's seen everything from the violent impacts of the late heavy bombardment to the emergence of life to the rise of intelligence. And it will be there, barring catastrophe, for billions of years to come, long after we're gone, long after our species has either evolved into something else or gone extinct or spread to other worlds. The moon will remain, will continue its slow drift away from Earth, will continue its orbit, will continue to stabilize Earth's climate, even if there's no one left to appreciate it. There's a kind of melancholy in that, isn't there? A reminder of impermanence, of our own fleeting existence against the backdrop of cosmic time. But there's also something beautiful, something reassuring about the moon's constancy, about the fact that it's been there all along, that it's part of the story of how we came to be, that it's still there, still doing its job, still making Earth habitable. The moon isn't just a rock in space, it's part of us, part of our history, part of what makes Earth what it is. And understanding that, understanding the secret history of the moon, the story of Theia and the giant impact and the debris disk and the formation of this unlikely companion, understanding how the moon stabilizes our planet and enables life and creates the tides and the night sky we've always known, understanding all of that gives us a deeper appreciation for the world we live in, for the cosmic coincidences and violent events and long, slow processes that made it all possible. So the next time you look up at the moon, the next time you see it hanging there in the sky, whether it's a thin crescent at sunset or a full moon rising over the horizon, brilliant and white and beautiful, think about what you're seeing. You're looking at a piece of Earth, or a piece of Earth and Theia mixed together, thrown into space by the most violent collision our planet ever experienced. You're looking at a world that was once molten, that cooled and solidified, and was bombarded by asteroids and erupted with lava, and then went quiet, geologically dead, frozen in time. You're looking at the object that stabilizes our climate, that gives us predictable seasons, that slows our rotation and raises our tides. You're looking at something that's been there since the beginning, since before life, since before oceans, since before anything recognizable as Earth existed. And you're looking at something that's moving away slowly, inexorably, changing the relationship between Earth and Moon, year by year, century by century, eon by eon. The moon is a clock, in a way, measuring deep time, marking the evolution of the Earth-Moon system from its violent birth to its eventual distant future. And it's a mirror reflecting sunlight, yes, but also reflecting back to us our own questions about origins and existence and meaning. Why are we here? How did we come to be? What circumstances, what events, what lucky accidents made it possible for a species like ours to arise on a planet like this? The moon is part of the answer to those questions. Not the whole answer, of course. There are many factors that make Earth habitable, many reasons why life arose here, and not, as far as we know, anywhere else in the solar system. But the moon is a crucial piece of the puzzle, a necessary component, something without which Earth would be fundamentally different, perhaps fatally different for complex life. And maybe that's the real secret history of the moon, the hidden story that we've only begun to uncover in recent decades. It's not just a story about a collision and a formation and an orbit. It's a story about interconnection, about how worlds shape each other, about how violent beginnings can lead to stable futures, about how accidents can become necessities. The moon and Earth are bound together, not just by gravity, but by history, by the shared experience of that cataclysmic impact, by billions of years of mutual influence, by the tides and the tidal locking and the orbital evolution that connect them still. They're a system, and understanding one requires understanding the other. We've learned so much about the moon in the past half century since we first went there, since we first brought back rocks and data and photographs. We've learned about its formation, its structure, its composition, its history. We've learned about the giant impact and the magma ocean and the late heavy bombardment and the volcanic flooding of the Maria. We've learned about its craters and its mountains and its ancient surface and its lack of atmosphere and its slowly changing orbit. But there's still so much we don't know, still so many mysteries waiting to be solved. The lunar swirls, the asymmetry between near and far sides, the details of the internal structure, the exact mechanisms of tidal evolution, the history of lunar magnetism, the distribution of water ice at the poles, the long-term stability of the Earth-Moon system under various perturbations. the ultimate fate of both worlds in the far future? These are questions that will drive lunar science for decades to come, questions that will be answered by new missions, new observations, new analyses, new theories. And as we answer those questions, as we continue to explore the moon both robotically and with human missions, as we perhaps establish a permanent presence there, as we use the moon as a base for deeper exploration of the solar system, we'll be writing the next chapter in the secret history of the moon, the chapter where humans become not just observers of that history, but participants in it, where we add our own story to the moon's story, where we become part of the ongoing evolution of the Earth-Moon system. That's a remarkable prospect, isn't it? For billions of years, the moon's story has been one of geology and physics and chemistry, of impacts and volcanism and orbital mechanics, all playing out without any conscious awareness, without anyone to observe or record or understand. But now there's us, and we do observe and record and understand, or at least we try to. And we're capable of acting, of changing things, of making choices that affect the future. What we do with that capability, how we use it, what kind of future we create, that's up to us. But whatever we do, whatever choices we make, the moon will still be there, still orbiting Earth, still pulling on our tides, still stabilizing our axis, still lighting up the night. The moon is patient, endures on timescales that dwarf human experience. It's seen Earth change from a molten ball to a world with oceans and continents and life and civilization, and it will see whatever comes next, whether that's humanity spreading to the stars or humanity going extinct or something in between. The moon doesn't care, doesn't have preferences, doesn't make judgments. It just is a natural satellite, a piece of rock and metal and mineral orbiting a planet, subject to the laws of physics and nothing else. And yet, it means something to us, has always meant something to us, because we're the kind of beings who create meaning, who tell stories, who look at the universe and see not just matter and energy, but beauty and mystery and wonder. The moon has inspired poets and artists and musicians and dreamers for all of human history. It's been a goddess and a god, a symbol of change and constancy, a marker of time, a source of romance, a destination for exploration, a challenge, a mystery, a companion. Every culture has moon stories, moon myths, moon calendars. The moon is woven into the fabric of human culture in ways that are difficult to fully articulate, because it's been there always, for as long as there have been humans to look up and see it. And now we know its secret history. Now we know where it came from and why it's there and what it does and how it's changing. That knowledge doesn't diminish the wonder, doesn't make the moon less beautiful or less meaningful. If anything, it increases the wonder, because now we understand not just what we see, but what it represents, the deep history, the violent birth, the crucial role in making Earth habitable, the ongoing evolution, the ultimate fate. The moon is a gift in a way, a gift from the chaos of the early solar system, a gift from a collision that could have destroyed Earth, but instead gave us something essential. It's a gift we didn't ask for, didn't design, didn't deserve through any merit or effort. It's just there, the result of physics and probability and the particular history of this one corner of the universe. But it's there, and it's ours, in the sense that we share a common origin, a common history, a common fate. Earth and moon, two worlds, different but connected, separated by 250,000 miles of empty space, but bound together by gravity and by the story of their formation. That's the secret history of the moon, the story we've uncovered through science and exploration and careful observation. And it's a story that continues, that's still being written, that will unfold over timescales we can barely imagine. We're privileged to live in a time when we can understand that story, can see the moon not just as a light in the sky, but as a world with a history, a world that matters, a world that's part of our own story in ways both profound and subtle. And maybe, just maybe, that understanding, that knowledge of the secret history of the moon can help us appreciate the fragility and the preciousness of our own world, can help us see Earth not as an infinite resource or a stage for human drama, but as a small, beautiful, improbable world in a vast universe, a world that owes its habitability in part to the companion that orbits it, the silent guardian that's been there from the beginning, that will be there long after we're gone, that connects us to the deep history of the cosmos and reminds us that we're part of something much larger, much older, much stranger, and more wonderful than we usually remember in our daily lives. Now let's move on to another theory for you to reflect on. I've been thinking a lot about physics lately, and there's this assumption we all kind of carry around without really examining it. We assume that physics, the fundamental rules that govern reality, are just, fixed, universal, unchanging, the same everywhere, at all times, for all eternity. And when you first think about that, it seems reasonable, right? I mean, if the laws of physics could just change on a whim, if gravity worked differently on Tuesdays, or if electrons decided to behave one way here and another way there, we'd be in chaos. The universe would be unintelligible, incomprehensible, utterly unpredictable. So we have to assume, that there are rules, and those rules stay the same. But here's the thing, and this is what keeps me up at night sometimes. What if that assumption is wrong? What if physics doesn't actually play by the rules we think it does? What if the game is different than we've been led to believe? Or what if the rules themselves can change? Or what if there are entirely different rules operating at scales or in domains we haven't yet explored? And that question, that possibility, it opens up something profound and frankly a little bit unsettling, because if physics can play by new rules, if the foundation of reality is more flexible or more complex or more strange than we've imagined, then everything we think we know becomes, provisional, uncertain. And maybe that's exactly where we find ourselves right now, at this moment in the history of science, standing at the edge of something new. You see, when we talk about the laws of physics, we're talking about something remarkably specific. We mean things like Newton's laws of motion, or Einstein's field equations, or the standard model of particle physics. These aren't just descriptions, right? They're mathematical frameworks that make incredibly precise predictions about how the universe behaves. And the remarkable thing, the thing that makes physics work as a science, is that these predictions turn out to be correct over and over again. You can calculate where Mars will be 6 months from now, and when 6 months pass, there it is, right where the math said it would be. You can predict the decay rate of a radioactive isotope, and it decays exactly as predicted. The laws of physics work. They're reliable. They're testable. They're the foundation of all modern technology, from the phone in your pocket to the satellites orbiting overhead. So when someone suggests that maybe physics plays by different rules, there's an immediate and understandable resistance. Because, look around. It works, doesn't it? The physics we have, the rules we've discovered, they explain so much. They've taken us from basic mechanics to quantum computers, from simple telescopes to detecting gravitational waves from colliding black holes billions of light years away. How can you argue with success like that? But here's where it gets interesting. And this is something that I think gets lost sometimes in the popular understanding of science. The fact that our current physics works, the fact that it makes accurate predictions, doesn't necessarily mean it's the complete story. It doesn't mean we've discovered all the rules, or that the rules we have are the final, ultimate truth about reality. In fact, the history of physics is a history of discovering that the rules we thought were fundamental were actually just approximations, special cases, useful but incomplete descriptions of a deeper, stranger reality. And that pattern, that recurring theme of thinking we had it figured out only to discover we were wrong, or at least not quite right, that should make us humble. It should make us wonder whether we're in the middle of that story right now, whether the physics we're so confident about today will look as quaint and limited to future scientists as Newton's mechanics looks to us. Think about Newton for a moment. Here's a guy who, in the late 1600s, basically invented modern physics. He looked at the motion of objects, the fall of an apple, the orbit of the moon, and he saw patterns, mathematical patterns, and he had the genius to realize that the same force that pulls the apple to the ground is the force that keeps the moon in orbit around the Earth. Gravity. One universal force governing both earthly and celestial phenomena. And he wrote down equations, beautiful equations, that describe this force with stunning accuracy. For more than 2 centuries, Newtonian mechanics was physics. It explained everything. It predicted planetary motions. It enabled the Industrial Revolution. It was the foundation of engineering and astronomy and, all of science, really. And the thing is, it worked. If you want to build a bridge or launch a cannonball or calculate the orbit of a comet, Newton's laws still work perfectly well today. They're not wrong exactly. They're just not the whole story. Because then along comes Einstein, right? Early 1900s. And Einstein starts thinking about light, and about how things behave when they're moving really fast, and about what gravity actually is. And what he discovers through a combination of thought experiments and mathematical reasoning that borders on the miraculous is that Newton's laws are actually wrong. Not wrong in the sense that they don't work for everyday situations, but wrong in a deeper sense. They're approximations, special cases that apply when things are moving slowly and gravity is weak. But when you push into extremes, when you look at objects moving close to the speed of light, or when you examine gravity near incredibly massive objects, Newton's rules break down. They give you the wrong answers. And Einstein's theory, special and then general relativity, these theories showed that space and time aren't separate, fixed backdrops against which physics plays out. They're part of the story. They're flexible, dynamic, curved by the presence of matter and energy. Gravity isn't a force in Einstein's picture. It's the curvature of space-time itself. And that's not just a different way of describing the same thing. It's a fundamentally different rule, a new rule. Physics, it turned out, plays by different rules than Newton thought. And here's what's so important about that transition, that shift from Newtonian mechanics to relativity. It didn't happen because Newton's laws stopped working for the things they'd always worked for. Bridges didn't suddenly collapse. The planets didn't veer off course. All the successful predictions and applications of Newtonian physics remained successful. What happened was that scientists started looking at new domains, new scales, new extremes. They looked at objects moving at very high speeds. They looked at light itself. They examined Mercury's orbit with incredible precision and noticed a tiny anomaly that Newton's laws couldn't quite explain. They wondered about the nature of space and time themselves, and in doing so, they discovered that the rules they thought were universal actually had limits. There were domains where different rules applied, not instead of Newton's rules, but more fundamental rules from which Newton's rules emerged as a special case, an approximation. Now, you might think, okay, that's interesting history, but surely we've got it figured out now, right? We have relativity, we have quantum mechanics, we have the standard model of particle physics. These are the real rules, the final rules. But that's not quite how it works. And this is where things get really fascinating, because we know with certainty that our current physics is still incomplete. We know it's still not the whole story. And we know this not because the theories fail in their domains of applicability, but because they fail when we try to put them together, when we try to extend them to new domains, when we look carefully at what they tell us about the universe and realize there are gaping holes in our understanding. The most obvious problem, the one that keeps theoretical physicists up at night, is that general relativity and quantum mechanics don't play well together. They're both incredibly successful theories. Relativity describes gravity, space-time, the large-scale structure of the universe, and it does so with remarkable precision. We've tested it over and over again. GPS satellites wouldn't work without relativistic corrections. We've detected gravitational waves, literal ripples in space-time, exactly as Einstein predicted a century ago. The theory works. Meanwhile, quantum mechanics describes the behavior of particles, atoms, light, all the fundamental constituents of matter and energy at the smallest scales. And it, too, has been tested to absurd levels of precision. The predictions of quantum electrodynamics, for instance, match experimental results to 10 decimal places or more. These are perhaps the two most successful scientific theories ever developed, but they're based on completely different principles, completely different mathematical frameworks. And when you try to combine them, when you try to create a theory of quantum gravity, you run into profound difficulties. The math breaks down. You get infinities where you should get finite answers. The theories seem fundamentally incompatible. And that tells us something important. It tells us that one or both of these theories, as successful as they are, must be incomplete. There must be a deeper theory, a more fundamental set of rules, from which both relativity and quantum mechanics emerge as approximations, special cases applicable in certain domains but not others. And whatever that deeper theory is, it's going to change the rules. It's going to show us that physics plays by different rules than either relativity or quantum mechanics suggest. We don't know what those rules are yet. We have candidates, theories like string theory or loop quantum gravity, but we don't have definitive evidence. We don't have that crucial experimental validation that would tell us we've found the right answer. We're in this strange position of knowing that our current physics is wrong, or at least incomplete, but not yet knowing what the right physics is. But it's not just about reconciling relativity and quantum mechanics. There are other hints, other clues scattered throughout modern physics that suggest we're missing something fundamental. Take dark matter, for instance. This is one of the great mysteries of contemporary cosmology. When astronomers look at galaxies, when they measure how fast stars are orbiting around galactic centers, they find something strange. The stars are moving too fast. According to Newton's laws, or even according to Einstein's relativity, if you know how much visible matter is in a galaxy, stars and gas and dust, you can calculate how fast objects should orbit. And what astronomers find is that the actual orbital speeds are much higher than the calculations predict. It's as if there's more mass there than we can see. A lot more. In fact, calculations suggest that about 85% of the matter in the universe is this invisible stuff that we can't detect directly. We call it dark matter because, well, we can't see it. It doesn't emit light, it doesn't absorb light, it doesn't interact with electromagnetic radiation at all, as far as we can tell. But it has to be there because its gravitational effects are undeniable. Now, the standard interpretation of dark matter is that it's some kind of particle we haven't discovered yet. Something that has mass, that participates in gravity, but that doesn't interact via electromagnetism. And there are good reasons to think this might be right. We've built incredibly sensitive detectors trying to catch dark matter particles, and while we haven't found them yet, the search continues. But here's the thing, and this is where the question of new rules comes in. What if dark matter doesn't exist? What if instead our theory of gravity is wrong? What if gravity doesn't actually work the way Einstein said it does, at least not on galactic scales? There's a theory, or actually a family of theories called modified Newtonian dynamics, or MOND, that explores this possibility. The basic idea is that maybe gravity doesn't follow the inverse square law at very large distances, or very weak accelerations. Maybe it behaves differently. And if you modify the equations just so, you can actually explain the rotation curves of galaxies without needing dark matter at all. Now, MOND has problems. It doesn't work as well for galaxy clusters. It struggles to explain certain cosmological observations. Most physicists think dark matter is the more likely explanation, but the mere existence of MOND, the fact that you can explain observations by changing the rules of gravity instead of adding invisible matter, that's significant. It shows that we have a choice in some sense. We can keep the rules and add new entities, or we can change the rules themselves. And we don't yet know with absolute certainty which approach is correct. And that uncertainty, that openness, it's a reminder that the rules of physics might not be as fixed as we think. Maybe gravity does play by different rules at different scales. Maybe the equations we use for the solar system aren't quite right for galaxies. Maybe there's a transition, a regime where gravity changes its character. And then there's dark energy, which is even stranger than dark matter. In the late 1990s, astronomers measuring distant supernovae made a shocking discovery. They found that the expansion of the universe is accelerating, not slowing down as you'd expect if gravity was the dominant force, but speeding up. Something is pushing the universe apart, and we have no idea what it is. We call it dark energy, and calculations suggest it makes up about 68% of the total energy content of the universe. That's astonishing, right? Roughly 95% of the universe, dark matter plus dark energy, is made of stuff we don't understand at all. We don't know what it is, we don't know where it comes from, we don't know why it exists, and that should be humbling. It should make us question whether we really understand the rules. The standard explanation for dark energy involves something called the cosmological constant, a term that Einstein actually added to his equations of general relativity and then later called his biggest blunder. But it turns out maybe it wasn't a blunder after all. Maybe there's this constant energy density pervading all of space, and maybe that's what's driving the accelerated expansion. But here's the problem. When physicists try to calculate what the value of this cosmological constant should be based on quantum field theory, they get an answer that's wrong by a factor of 10 to the power of 120. That's not a typo. 120 orders of magnitude. It's arguably the worst prediction in the history of physics, and that mismatch, that enormous discrepancy between theory and observation, it suggests very strongly that we're missing something fundamental about how quantum mechanics and gravity fit together. Maybe the rules we're using to calculate vacuum energy are wrong. Maybe there's some mechanism we don't understand that sets the cosmological constant to its observed value. Maybe the very concept of vacuum energy needs to be rethought. We don't know. But what we do know is that our current physics can't explain it. Let me take you in another direction for a moment, because there's another aspect to this question of new rules that's equally fascinating. We've been talking about domains where our current physics seems incomplete, places where we know there are gaps in our understanding. But there's also the possibility, the philosophical possibility really, that the rules of physics themselves might not be as absolute as we think. What if the laws of physics could be different in different places, or at different times, or in different universes? That sounds like science fiction, I know, but it's actually a serious question that physicists and cosmologists wrestle with. It's related to something called the fine-tuning problem. The fine-tuning problem goes like this. There are a bunch of constants in physics, fundamental numbers that show up in our equations. Things like the strength of gravity, the mass of the electron, the speed of light, the fine structure, constant. And what physicists have noticed is that these constants seem to be very precisely tuned to allow for the existence of complex structures like atoms, stars, planets, and ultimately life. If you change some of these constants even slightly, like if you make gravity a little bit stronger or the electromagnetic force a little bit weaker, you end up with a universe that's radically different and generally much less hospitable. Stars might not form, or they might burn out too quickly. Atoms might not be stable. Chemistry as we know it might not be possible. And that raises a question: why are the constants what they are? Why do they have these very specific values that allow for a universe as interesting and complex as ours? One possible answer is the anthropic principle, which basically says, well, of course the constants are tuned for life, because if they weren't, we wouldn't be here to observe them. It's a selection effect. If there are many universes or many regions of one vast universe, each with different values of the fundamental constants, then we necessarily find ourselves in one of the rare regions where the constants allow for observers to exist. It's not that the constants were designed or fine-tuned for us. It's that we can only exist in regions where the constants happen to have the right values. Right. And this idea, this anthropic reasoning, it's controversial, but it's taken seriously by many physicists because it might actually be testable if we can develop a good theory of how different universes or different regions come to have different constants. And that brings us to something like string theory, or more generally, theories that try to unify all of physics into one comprehensive framework. String theory, if you've heard of it, is this idea that the fundamental constituents of reality aren't particles, but tiny vibrating strings. Different vibration modes of these strings correspond to different particles: electrons, quarks, photons, gravitons. And string theory, in its various forms, requires extra dimensions of space beyond the three we experience. 6 or 7 extra dimensions, all curled up so small that we can't detect them directly. Now, one of the interesting features of string theory is that the way these extra dimensions are curled up, the specific geometry of this compactification, determines the values of the constants we observe in our 4-dimensional world. And there are a lot of ways to curl up extra dimensions, like a lot. Estimates suggest there might be 10 to the 500 or more different possible configurations, each giving rise to different physics, different constants, different rules. And this is what's called the landscape problem in string theory. If there are 10 to the 500 different possible universes or different possible phases of one universe, each with different rules, then string theory doesn't really predict the rules we observe. It just says there are many possibilities, and we happen to be in one of them. And some physicists find that deeply unsatisfying. They wanted string theory to predict the values of the constants, to tell us why the electron has the mass it does, why gravity has the strength it does. Instead, it seems to say, well, it could be anything, and somewhere in the vast landscape of possibilities, it is everything. Our universe, with its particular set of rules, is just one among countless others. But let's think about what that means, because it's actually profound and maybe a little bit vertiginous. If the landscape picture is right, if there really are many universes or many domains, each with different physics, then the rules of physics aren't universal in an absolute sense. They're local, they're contingent, they depend on which universe or which region you happen to be in. In some other universe, gravity might be much stronger. In another, there might be 4 fundamental forces instead of our 4 or 6 or 2. Particles might have different masses. The speed of light might be different. Hell, light might not even exist in some universes if electromagnetism doesn't. The entire structure of physical law could be radically different. And our universe, with our physics, is just one particular implementation, one particular set of rules selected from an enormous space of possibilities. Now, I want to be clear, this is speculative. We don't have direct evidence for other universes or for the string theory landscape. These are ideas that come out of our attempts to extend our theories beyond what we can currently test. But the mere fact that these ideas are taken seriously, that they arise naturally from theoretical attempts to unify physics, that's telling. It suggests that the question, what if physics plays by new rules, isn't just about undiscovered phenomena or extensions of our current theories. It might be about the very nature of physical law itself. Maybe the rules aren't as fixed, as absolute, as timeless as we've always assumed. And there's another angle here, another way that physics might play by new rules, and it has to do with emergence. This is the idea that new rules, new laws, new patterns of behavior can arise at different scales or levels of organization, rules that aren't simply reducible to the fundamental laws of the underlying constituents. Think about it this way. You take a bunch of atoms, right? At the level of individual atoms, the rules are quantum mechanical. Atoms behave according to the Schrödinger equation. They have quantized energy levels. They exhibit wave-particle duality, all that weird quantum stuff. But when you put billions and billions of atoms together, you get, say, a block of ice. And ice has properties, bulk properties like hardness and crystal structure and thermal conductivity that simply don't exist at the level of individual atoms. These are emergent properties. They arise from the collective behavior of many atoms, but you can't predict them, not easily anyway, just by looking at one atom. And the interesting thing is that we can describe the behavior of ice using macroscopic laws, thermodynamics, and material science, without explicitly solving the quantum mechanics of every single atom. We have effective theories, simplified rules that work at the scale of bulk matter. And these effective theories are real. They make predictions. They're useful. Engineers use them to design structures, but they're not the fundamental rules. They're emergent rules that apply at a particular scale. And maybe, just maybe, the laws of physics that we think of as fundamental aren't really fundamental at all. Maybe they're emergent from something deeper, something we haven't yet discovered. Maybe space-time itself is emergent. Maybe the particles and forces we see are effective descriptions of some underlying substrate that behaves according to entirely different rules. Rules we can't yet access or understand because we're stuck looking at things from the emergent scale. This is actually an active area of research. Some approaches to quantum gravity, like loop quantum gravity or theories based on quantum information, suggest that space-time might not be fundamental. It might be an emergent structure arising from something more basic, maybe a network of quantum relationships or qubits or some other mathematical structure. And if space-time is emergent, then the laws of physics that we observe, which are formulated in terms of space and time, might also be emergent. They might be approximations, effective rules that apply in the regime where space-time looks smooth and continuous, but that break down when you probe deeply enough. And what are the fundamental rules underneath? We don't know. That's the frontier. That's the edge of our understanding. Let me shift gears slightly and talk about quantum mechanics itself, because quantum mechanics is already a place where physics plays by rules that are radically different from what we experience in everyday life. I mean, the rules of quantum mechanics are bizarre. Particles can be in superpositions, existing in multiple states at once until they're measured. Particles can be entangled, such that measuring one instantaneously affects another, no matter how far apart they are. The act of measurement seems to have a special role, collapsing the wave function and forcing nature to choose one outcome from many possibilities. And there's this fundamental uncertainty, Heisenberg's uncertainty principle, that says you can't simultaneously know certain pairs of properties with arbitrary precision. It's not that we lack the tools to measure precisely, it's that the universe itself is fundamentally indeterminate at the quantum level. Now, quantum mechanics works. It's the foundation of modern technology. Semiconductors, lasers, MRI machines all depend on quantum effects. The theory makes predictions that have been confirmed to incredible precision. But here's the thing, we don't really understand it. Or rather, we understand how to use it, how to calculate with it, how to make predictions, but we don't understand what it means. What's really happening when a particle is in a superposition? What is the wave function? Is it a real physical thing or just a mathematical tool for calculating probabilities? And what happens during measurement? Why does the wave function collapse? And what counts as a measurement? These are questions that have been debated for nearly a century, and there's still no consensus. There are many different interpretations of quantum mechanics, the Copenhagen interpretation, many worlds, pilot wave theory, each offering a different picture of what's really going on, and we have no definitive way to choose between them. And that's strange, right? We have this theory that works brilliantly, but we don't agree on what it's telling us about reality, and it raises the possibility that maybe we haven't found the right way to think about quantum mechanics yet. Maybe there's a deeper theory, a more complete theory that would make sense of all the weirdness. Maybe quantum mechanics, as we currently formulate it, is an approximation or a special case of some broader framework. And that broader framework might involve new rules, new principles that go beyond what we currently understand. There have been various proposals over the years. Some people think quantum mechanics needs to be modified to explain the measurement problem. Some think there are hidden variables we haven't discovered. Some think consciousness plays a role. Some think there's an objective collapse mechanism. We don't know. But the fact that we're still arguing about the foundations of quantum mechanics 100 years after its discovery, that's a sign that maybe we're missing something fundamental. And then there's the issue of time. Time is one of the strangest concepts in all of physics. And depending on which theory you're using, time behaves very differently. In classical mechanics, Newtonian mechanics, time is absolute. It flows uniformly everywhere, the same for everyone. It's like a universal clock that ticks away independently of what's happening in the universe. But Einstein's relativity changed that. Time became relative. Different observers moving at different speeds experience time differently. Time dilates near massive objects. Time is not separate from space, but part of this unified space-time fabric. And there's no absolute now, no universal present moment. What's simultaneous for one observer isn't simultaneous for another. Time, in relativity, is much more flexible and observer-dependent than Newton ever imagined. But then quantum mechanics comes along and treats time completely differently. In quantum mechanics, time is not an observable. It's a parameter. It's treated asymmetrically compared to space. And when you try to make quantum mechanics work in a relativistic context, when you develop quantum field theory, you get strange things like particles traveling backward in time, antiparticles interpreted as particles going the other direction through time. And then when you try to develop a theory of quantum gravity, time becomes even more mysterious. Some approaches suggest that time might not be fundamental at all, that it might be an emergent phenomenon, something that arises from more fundamental quantum relationships. There are even proposals for a timeless physics, a formulation where time doesn't appear in the fundamental equations but emerges as an approximate concept in certain regimes. So, what is time, really? Is it fundamental or emergent? Is it absolute, relative, or something else entirely? Does it have a direction, an arrow, or is that just a consequence of entropy and the second law of thermodynamics? Can it change speed, stop, reverse? These aren't idle philosophical questions. They're questions about the rules of physics, about how the universe actually works. And different theories, different approaches to fundamental physics give different answers, which suggests that we haven't yet figured out the right rules when it comes to time. Maybe time does play by different rules than we think. Maybe there are regimes, situations, where time behaves in ways we haven't anticipated. Let's talk about causality for a second, because causality is deeply tied to time, and it's another place where the rules might be more flexible than we assume. In classical physics, causality is straightforward. Events have causes that precede them in time. A cause is B, and B happens after A. You can't have an effect without a cause, and causes always come before effects. That's just how the world works, or so it seems. But quantum mechanics complicates this. In quantum entanglement, measuring one particle seems to instantaneously affect another particle, even if they're light years apart. Does that violate causality? Most physicists say no, because you can't use entanglement to send information faster than light, so you can't create a causal paradox. But it's weird. It suggests that the universe is connected in ways that don't fit neatly into our classical picture of cause and effect. And then there are things like quantum tunneling, where a particle can pass through a barrier that it classically shouldn't be able to cross. In some interpretations, the particle is on both sides of the barrier at once in a superposition until measured. But how long does the tunneling take? Can you even assign a duration to the process? Some analyses suggest that the tunneling time is 0 or even negative, which would seem to violate causality. But the math works out such that you still can't send information faster than light. So it doesn't create actual paradoxes. It's just deeply counterintuitive. It suggests that at the quantum level, the notion of a clear causal sequence, A happening then B happening, becomes blurry. Events become probabilistic. Causality becomes more like a statistical tendency than an iron law. And in some speculative theories, causality might break down entirely in certain situations. In theories with closed time-like curves, solutions to Einstein's equations that in principle allow for time travel, you could have events that are both causes and effects of themselves. Causal loops. Now, most physicists think these solutions are probably not physically realizable, that there's some mechanism, some quantum effect perhaps, that prevents closed time-like curves from actually existing. But the fact that they're allowed by the equations, that's interesting. It means the rules, as we currently understand them, don't absolutely forbid time travel. They make it very difficult, maybe impossible in practice, but the door isn't completely closed. And if time travel were possible, if you could have causal loops, then the rules of causality would have to be rewritten. Cause and effect would become tangled in ways we can barely imagine. Now, I want to circle back to something I mentioned earlier, the idea of varying constants, because there's actually been serious scientific investigation into whether the fundamental constants of nature might change over time or differ in different places. It sounds crazy at first. If the speed of light or the strength of gravity or the mass of the electron could just change, wouldn't that throw everything into chaos? But the question is whether they change on timescales and scales that we can detect. If the fine structure constant, which governs the strength of electromagnetic interactions, changed by 1 part in a billion per year, that's a tiny change, but over billions of years, over the age of the universe, it might be detectable. And scientists have actually looked for this. They've analyzed light from distant quasars, light that's been traveling for billions of years, looking for tiny shifts in spectral lines that would indicate that the fine structure constant was different in the distant past. And the results are, well, inconclusive. Some studies claim to see small variations, others see nothing. The effects, if they exist, are right at the edge of what we can measure. But the mere fact that we can contemplate this, that we can look for it, that's significant. Because if the constants do vary, even slightly, it means they're not truly constant. They're dynamical. Their fields may be something that can change over time or space. And that would be a profound shift in how we think about physics. Constants wouldn't be constants. They'd be variables. And we'd need new rules, new equations to describe how these variables evolve. It would mean that the laws of physics we observe today might be slightly different from the laws that govern the early universe, or that govern distant regions of the cosmos. The rules would be local, time-dependent, contingent. There's this concept in cosmology called eternal inflation, which is an extension of the standard inflationary model of the early universe. The basic idea of inflation is that the universe underwent a period of incredibly rapid expansion very early on, faster than the speed of light, driven by some kind of energy field. This solves a bunch of problems in cosmology, explains why the universe is so uniform on large scales, why it's flat, all sorts of things. But in eternal inflation, the idea is that inflation never completely stops. In most regions, the energy field that drives inflation decays and inflation ends, and you get a pocket universe like ours where normal expansion takes over. But there are always regions where inflation continues, spawning new pocket universes, which themselves can spawn more universes forever. It's an infinite, eternally growing multiverse of pocket universes. And here's the kicker. In different pocket universes, the decay of the inflaton field, the field driving inflation, might happen in different ways, leading to different vacuum states, different configurations of fields and forces. The fundamental constants, the particles, the forces, The rules of physics could all be different in different pocket universes. Our pocket, our observable universe, has one set of rules. Another pocket, a billion light years beyond our horizon, might have completely different rules. And we could never visit those other pockets, never observe them directly because they're expanding away from us faster than light. But they'd still be real, at least according to the theory. And in this picture, the rules of physics aren't universal. They're local to our pocket. Elsewhere, in vast regions of the multiverse that we can never access, physics plays by entirely different rules. Now, is this true? Is eternal inflation correct? Do other pocket universes exist? Honestly, we don't know. There's no direct evidence. It's an extrapolation from our best theories, but we can't test it, not with current technology. And that frustrates a lot of physicists. Science is supposed to be about testable predictions, and if you're talking about regions of space-time that are forever beyond our ability to observe, are you even doing science anymore, or have you crossed over into metaphysics? It's a legitimate concern. But at the same time, these ideas emerge naturally from theories that do make testable predictions, theories that we have good reasons to take seriously. So maybe we need to expand our notion of what counts as scientific. Maybe the rules of evidence need to adapt to the realities of modern cosmology and fundamental physics. Let me talk about another way that physics might play by new rules, and this one is really wild. It's the idea that the universe might be discrete rather than continuous. In our everyday experience, and in most of our physical theories, space and time are treated as smooth, continuous. You can divide space into smaller and smaller regions infinitely, and time into smaller and smaller intervals infinitely. There's no smallest distance, no smallest duration. You can always zoom in further. But what if that's not true? What if there's a fundamental granularity to space-time, a smallest possible unit, a kind of pixel or atom of space and time? This idea goes back to Max Planck, who proposed the Planck length, about 10 to the minus 35 meters, as a natural unit of length that falls out of combining the fundamental constants of quantum mechanics and gravity. And some theories of quantum gravity, particularly loop quantum gravity, take this seriously. They propose that space-time itself is made of discrete quantum units, tiny loops or nodes in a network, and that below the Planck scale, the smooth space-time of general relativity breaks down. Space becomes grainy, discrete. If space-time is discrete, then the rules change. You can't have infinite precision. You can't zoom in forever. There's a fundamental limit to how small things can be, how short time intervals can be. And that might solve some of the infinities and divergences that plague our attempts to quantize gravity. But it also means that at the most fundamental level, the universe operates more like a digital computer than a smooth continuum. It's ticking along, evolving from one discrete state to another. And the rules governing these discrete states might be very different from the differential equations we use to describe smooth, continuous systems. Maybe the fundamental rule is more like a cellular automaton, a set of discrete update rules that determine how the configuration of space-time evolves from one tick to the next. That's a radically different picture from the smooth geometry of general relativity or the continuous wave functions of quantum mechanics. And along similar lines, there's this growing idea that information might be more fundamental than matter or energy, that physics is really about information processing. This comes out of work on black hole thermodynamics and the holographic principle. Black holes, it turns out, have entropy, they have a temperature, and they emit radiation, Hawking radiation. And the amount of entropy a black hole has is proportional not to its volume, but to the area of its event horizon. That's weird. It suggests that the information content, the number of possible states, scales with area rather than volume. And this led to the holographic principle, which says that the information in any region of space can be encoded on the boundary of that region like a hologram. The three-dimensional physics inside might be equivalent to a two-dimensional theory on the boundary. Now, if that's true, if holography is a fundamental principle, then maybe our familiar three-dimensional space is not the fundamental reality. Maybe it's a projection, an emergent description of something more basic happening on a lower dimensional boundary. And if physics is fundamentally about information, about qubits or quantum states or whatever the basic unit is, then the rules might be more akin to the rules of quantum computation than to the differential equations of classical field theory. Space and time and matter might all be emergent from underlying information theoretic principles, and that would change everything. It would mean that the rules we use, the equations of motion, the conservation laws, they're all approximations, effective descriptions of an underlying information processing system that plays by completely different rules. This is deeply speculative, I know, but the point is that there are serious physicists, serious researchers exploring these ideas because they offer potential ways forward in problems where our current physics is stuck. When you can't reconcile quantum mechanics and gravity, when you encounter infinities and paradoxes, you start wondering if the problem is that you're using the wrong framework, asking the wrong questions, looking for the wrong kind of rules. Maybe the universe doesn't work the way we've been assuming. Maybe the rules are fundamentally different from what we've imagined. And maybe we need to be willing to let go of our preconceptions and explore radically new possibilities. Now, let's think about what it would actually mean, practically and philosophically, if physics does play by new rules. First, practically, if we discover that our current theories are wrong or incomplete in some fundamental way, that would open up new technological possibilities. General relativity gave us GPS satellites. Quantum mechanics gave us computers and lasers. What would a theory of quantum gravity give us? We don't know. Maybe nothing practical. Maybe something we can't even imagine right now. But history suggests that deep understanding of physics tends to lead eventually to technological applications. If we learned that space-time is discrete, or that information is fundamental, or that there are extra dimensions that knowledge might enable entirely new technologies, new ways of manipulating reality. But beyond the practical, there's the philosophical dimension, and this is where things get really interesting to me. Because our understanding of physics shapes our understanding of reality itself. It tells us what's real, what's possible, what the universe is made of, how it works. And if the rules change, if we discover that reality operates by principles we never anticipated, that shifts our entire worldview. It changes what we think is possible. It changes how we think about ourselves and our place in the cosmos. And maybe it makes the universe a little more mysterious, a little less deterministic, a little more open. There's something deeply human about the desire to find the ultimate rules, the final theory, the equation that explains everything. Einstein spent the last decades of his life searching for a unified field theory that would bring together all of physics. Physicists today talk about the search for a theory of everything, a single framework that encompasses all forces, all particles, all phenomena. And there's a kind of beauty in that goal, a hope that beneath all the complexity and diversity of the universe, there's a simple, elegant set of rules from which everything else follows. But maybe that's not how it works. Maybe there is no final theory. Maybe the rules keep changing as you look at different scales, different regimes. Maybe there are layers upon layers of emergent phenomena, each with its own effective rules all the way up and all the way down. Maybe the universe is more like an onion with endless layers than like a pyramid with a single foundation. Or maybe the rules are contextual. Maybe they depend on the observer, on the frame of reference, on the scale at which you're looking. We already know this is true to some extent. The rules of thermodynamics are different from the rules of quantum mechanics, even though thermodynamics emerges from the statistical behavior of quantum systems. The rules that govern an individual electron are different from the rules that govern a mole of electrons in a wire. And maybe that pattern continues. Maybe at the Planck scale, if we ever access it, the rules are completely different from anything we've encountered. Maybe in the very early universe, at energies far beyond anything we can recreate, physics was different. Maybe in the interior of black holes, beyond the event horizon, the rules break down and something new takes over. And here's a thought that I find both exhilarating and a little bit terrifying. If the rules of physics can be different, if they're not absolute and eternal, then in some sense the universe is more creative, more generative, more unpredictable than we thought. It's not just executing a predetermined program running on fixed rails laid down at the beginning. It's exploring possibilities, it's generating novelty. And maybe we're part of that process, not just passive observers trying to decode the rules, but active participants in a universe that's still, in some sense, making itself up as it goes along. I don't want to overstate that. The universe clearly isn't arbitrary. There are patterns, regularities, laws that hold with stunning consistency. We're not living in a chaotic fever dream where anything goes. But within the structure, within the patterns, there might be more flexibility, more possibility than we've traditionally assumed. The rules might be more like guidelines, strong tendencies that admit of exceptions, variations, evolutions. And if that's true, then the project of physics isn't just about discovering what the rules are. It's about understanding how the rules come to be, how they might change, what determines the rules in the first place. There's a term that some philosophers and physicists use called nomological conventionalism, which is a fancy way of saying that the laws of nature might be conventions, not necessities. They might be contingent facts about our universe rather than logical truths that couldn't be otherwise. And if laws are contingent, then in principle, they could have been different and might be different elsewhere. We happen to live in a universe with these laws, but other universes or other phases of our universe might have different laws. And that raises the meta question: what determines which laws obtain? Is there a meta law, a rule that governs which rules apply? And if so, what determines the meta law? Do we end up in an infinite regress, or is there some stopping point, some ultimate principle that's just brute fact? These are deep questions, and I don't pretend to have answers. I'm not sure anyone does. But they're questions worth asking because they force us to examine our assumptions about the nature of physical law, about what we mean when we say we understand the universe. And in a way, this is the most profound version of the question, what if physics plays by new rules? It's not just asking whether we've discovered all the rules yet, whether there are more phenomena to explain, more equations to write down. It's asking whether the very concept of a rule, a law, is the right way to think about the universe. Maybe reality is more fluid, more context dependent, more fundamentally open than the notion of fixed laws suggests. Now, you might be thinking, okay, this is all very abstract and speculative, but what does it actually mean for me, for my life, for how I experience the world? And that's a fair question, because for everyday purposes, the physics we have works just fine. Apples still fall down, the sun still rises, your car engine operates according to well-understood principles. None of that changes whether or not there are extra dimensions or a multiverse or discrete space-time at the Planck scale. But I think there's something important here, something that goes beyond the practical. It's about humility, about recognizing the limits of our knowledge, about staying open to the possibility that we're wrong. Throughout history, people have thought they had reality figured out. The earth is flat and the center of everything. The sun revolves around us. Space and time are absolute. Atoms are the smallest indivisible units. Each time we were wrong, not completely wrong. Our theories captured something real, something true in a limited domain, but wrong in thinking we had the final answer, the complete picture. And we're probably making the same mistake now. Our current physics is incredibly successful, yes, but it's also clearly incomplete. We know it's incomplete. We know there are things it doesn't explain, regimes where it breaks down, questions it can't answer. And that means almost certainly that future physics will look different. The rules will change, not invalidated necessarily, but subsumed into a broader framework seen as approximations or special cases of something deeper. And when that happens, when the rules change again, as they inevitably will, I hope we remember this moment. I hope we remember that physics is a human endeavor, a process of successive approximation, an endless journey toward understanding that may never reach a final destination. The universe doesn't owe us comprehensibility. It doesn't guarantee that our brains, evolved to navigate a middle-sized world at medium speeds, are capable of grasping the ultimate nature of reality. Maybe we'll keep discovering new layers forever. Maybe we'll hit limits, things we simply can't understand with our current cognitive architecture. Maybe we'll need to augment ourselves, build machines that think in ways we can't, to push the boundaries further. Or maybe, just maybe, we'll find that the universe is stranger and more wonderful than we ever imagined, that the rules we thought were fixed are actually just one possibility among many, and that the deepest truth is not a set of equations, but something more fundamental, more beautiful, more mysterious. I think about this sometimes when I look up at the night sky, at the stars and planets and galaxies, all that vast structure stretching out for billions of light years. We understand so much. We know the stars are nuclear furnaces powered by fusion. We know the galaxies are held together by gravity and dark matter. We know the universe is expanding, accelerating, evolving according to the equations of general relativity and cosmology. But we also know that our understanding is incomplete. We know that at the smallest scales and the largest scales and the highest energies, our theories break down. We know there are questions we can't answer, phenomena we can't explain. And maybe that's okay. Maybe the point isn't to have all the answers. Maybe the point is to keep asking questions, to keep probing, to keep wondering. Because here's the thing about physics, about science in general. It's not a collection of facts. It's not a static body of knowledge. It's a process, a method, a way of engaging with the world. It's based on the idea that reality is knowable, that there are patterns we can discover, that observation and experiment and reason can lead us toward truth. But it's also based on the idea that we can be wrong, that our theories are always provisional, always subject to revision in light of new evidence. That's the beauty of science. It's self-correcting, it's humble, it admits when it doesn't know, it changes its mind when the data demands it. And if physics plays by new rules, if we discover that our current understanding is incomplete or wrong in some fundamental way, science will adapt. We'll revise our theories, we'll develop new mathematics, we'll build new experiments, we'll keep pushing forward. And that's why I find this question so compelling, so important. What if physics plays by new rules? It's not just an abstract intellectual puzzle. It's a reminder that we're still exploring, still discovering, still learning. It's an invitation to think differently, to question assumptions, to imagine possibilities beyond what we currently know. It's a call to intellectual humility and courage, to admit what we don't know, while still pushing forward to learn more. And maybe that's the real lesson here. The rules of physics might change, or we might discover that they were never what we thought they were. But the process of discovery, the human drive to understand, that remains constant. That's the one rule that doesn't change, the one principle that guides us forward, no matter how strange or counterintuitive the universe turns out to be. So when someone asks, what if physics plays by new rules? I think the answer is both simple and profound. Of course it does, it always has. Every major advance in physics has been a discovery that the rules were different from what we thought. And it will happen again. We'll find new rules, deeper rules, stranger rules. We'll revise our theories and expand our understanding. We'll push the boundaries of knowledge further out into the unknown, and the universe will keep surprising us, keep revealing new layers of complexity and beauty and mystery. Because that's what the universe does. It's not a finished product, a solved puzzle. It's an ongoing revelation, a never-ending source of wonder. And our job as curious beings, as scientists, as humans, is to keep exploring, keep questioning, keep learning, to stay open to the possibility that everything we think we know is just the beginning, just the first chapter in a story that's far stranger and more beautiful than we can yet imagine. And maybe in the end, that's the most important rule of all. Not a rule about gravity or quantum mechanics or space-time, but a rule about how to approach the unknown, how to live with uncertainty, how to find meaning in a universe that may never fully reveal its secrets. Stay curious, stay humble, stay open to surprise. Because if there's one thing the history of physics teaches us, it's that the universe is full of surprises and the rules are always more interesting than we expected.